day. We continue our lecture on design of shafts, and this is lecture number 35. In the last class, we have been discussing about the hydrodynamic theory of lubrication. So, what in short I have written hydrodynamic theory. And just a recapitulation that this particular hydrodynamic theory, the historical background is that from the experimental investigations of Petrov and Tower and looking at their interesting results, what happened that Reynolds suggested a general equation for the hydrodynamic theory, and this equation is given here. As you can see, this equation is nothing but purely a flow equation under the pressure gradient, and that is for the left hand side, and the corresponding right hand side is some sort of device or some sort of pressure generation mechanisms that we will talk about. In this particular equation, what has been assumed is that the lubricant is incompressible, and the wedge shaped what we have been talking about earlier has been assumed to be a somewhat a straight profile. Okay, this is the wedge if we consider, and this is the converging passage through which the lubricant is flowing. Now, here essentially the variation of pressure is in the, if we consider, I think it is the first thing is that we give the coordinate axis. This is the x, y, and this comes out to be z. So, bearing is very long in this z direction, and in this case the pressure variation is only in the x and z direction, and essentially remains same in this particular y direction. And once again, as already I have told, that the lubricant has been assumed in this equation to be an incompressible one. And with this assumptions, the very well known Reynolds equation stands like this, which is basically, as I told you, is a flow equation. Now, let us have a look of this particular right hand term in details. Okay. So, what we look at the right hand term, if we see, then what is happening, that if there is two moving surfaces, say this is 1 and this is 2, and for which at point 1 and point 2 your velocities are u1, u2, u1, v1 and w1 respectively, which is in this direction, and in the point 2 also we are having the velocities as v1, u2, v2 and w2 respectively. So, in this case, general form of the equation is as given over here. This is the term in with respect to the delta x, this is with respect to the y, and these are other two terms that is coming into picture. Now, if we consider this expression and take the partial derivative only for this particular part, say just we are taking up this part and give the partial derivative of this one, then we will be getting an expression of this sort of, and this plus dot dot means all other terms are present over here. Now, in this case we are replacing this u1 plus u2, okay, as a capital U. Now, you see this particular term is called, as it is been given, a physical wedge. What is that? That particular wedge action, that means how the wedge, this h is the film thickness, and that is how it is changing with respect to x, and that has got a name which is called a physical wedge. So, this is one of the pressure generation mechanism. This is also called a stretch. This particular term is called stretch, where the how the flow velocity, I mean the velocity is changing with respect to x, and this is another term in this expression which gives you how the variation of lubricant density is taking in the directions of x. Well, as I told you that it is an generalized equation where all these variations of density variations etc., are also taken care of. Now, this is also another very important term, that with respect to time how the film thickness is changing, and that is actually called a term called squeeze film. And the last one, how the compression is taking place with respect to time, and that is simply it is termed as a compression. Now, in the present case of the Reynolds equation, you do not find all these terms in the right hand side. As a matter of fact, just have a look. We will be only considering this particular term which is called the physical wedge. Well, so we consider this term physical wedge. Okay, this is the term we are considering in the present case of journal bearing, whereas the other terms are also applicable in some other applications. Well, so we understand that this is an idea which gives us the physical concept of how the pressure generation mechanism works for a flow problems, when for a basically for a flow through an converging passage, and that gives us the total idea of the Reynolds equation, and that is what we once again look at to this one. Okay. So, this is the equation. Now, we come down to this basic equation. So, as I was telling you, this is one of the very basis for design of a journal bearing. Now, we come down to the idea of the journal bearing design. The steps in journal the journal bearing designs are like that. What you have to find out basically is the bearing pressure. If you know the bearing pressure, you know the what is the load capacity. That means, how much load this particular bearing can carry. So, for finding out that, one has to find out what? One has to look for the operating conditions, okay, temperature, speed, etc. Then the geometrical parameters and the lubricant. These are the basic three things what we will be finding out in the journal bearing design, and once we can finalize this particular parameters, then we get a bearing pressure. Okay. So, once we find out this bearing pressure, then we know what will be the load carrying capacity. Now, after all these design parameters being selected, one very important situation comes, that you have to check for the proper design zone. Okay. This word what has been used over here really requires some little bit of explanation, and let us come down to the idea that what we mean by this design zone. Now, this is the one of the plot you can see of the coefficient of friction versus bearing characteristic number. So, what is this bearing characteristics number? This is a non-dimensional parameter which comes out to be in the form viscosity, speed of the bearing and the pressure. Okay. So, this pressure is, as a matter of fact, the projected pressure. Means what is that one? I think I should have explained you. This is the thing. Now, if this is a bearing and it is acted upon by some load capital P, if we consider, then this is the diameter of the bearing. So, that P is the total P divided by the projected area, that means this is the D into L, that okay. So, this is the projected area that gives you the pressure of the bearing. So, considering this particular fact, we come down to this, what we understand by this this particular plot. This plot has been taken from the test results of Mackey brothers, and this shows a very important characteristics of journal bearing design. See, in this particular case, there is a demarcation line up to this one. So, up to here, you know, with the increasing bearing characteristics number, the curve goes on increasing, whereas the friction goes on increasing, sorry, and here with the reduction of bearing characteristics number, the friction goes on increasing. So, here this is the limit, and beyond this limit we call this is a boundary lubrication, or sometimes it is also termed as imperfect lubrication also. Imperfect lubrication means in this boundary lubrication there won't be a very definite film lubricant film present, there will be a metal to metal contact, and some sort of an oiliness sort of thing might be also present over there. So, this is what we called as boundary lubrication, and this particular portion from B to D what we called as hydrodynamic lubrication. Now, once we look into the design zone, means is that the calculated bearing characteristics number should be somewhere in this design, somewhere in this zone of C to C to D. Well, we can talk about B to D also, but why not, just I am just telling it. What happens that say in any point over operating point you consider over here, then what is happening that in this particular case you are having an given viscosity, speed and the pressure. So, these two parameters are not changing. Suppose by continuous movement what is happening, the due to some friction, suppose what will happen, certain amount of temperature generation is there. So, suppose if there a temperature rise is taking place, then what will happen, that immediately the viscosity of the lubricant will be falling down. Okay. So, as it is falling down, immediately what will happen, the bearing characteristics number instead of at this location, say it is coming out of this location. So, this particular one goes down, operating point goes down here. So, resulting in what, lowering of the friction. So, the moment there is a lowering of friction, then automatically temperature decreases, and again bearing comes down to this particular value. Again it can go up, but anyway it has got a self controlling phenomena, somewhere a self control phenomena is there. So, that is the reason what happens, that people consider this zone to be the design limit. However, one thing is there, although we can see that normally from here to here we could have chosen our design zone, but design lower limit is somewhat kept at C, which is roughly around 5 times from this particular value. Okay. Or in other words, we can just say that it should be sufficiently away from this particular zone. So, there is no possibility by any means that this particular design point goes on this one. So, on the contrary, what you can see is that the reverse will happen. If there is by chance there is an reduction in bearing characteristics number, the friction goes on increasing, means more and increasing of the temperature takes place, and that is what we consider the bearing becomes unstable in operation. So, now I think you hope you understand that what we mean by the design zone. Well, so as we see that this was the test result of Mackey, we have described about the design zone. So, this design zone is clear to you. Now, we come down to the two methods very popularly used for bearing design. The first method developed by AMD Hersey and the second method developed by A. Raimondi and J. Boyd. But this particular method, what we call as the first method, is relatively old. More people do by the second method. Anyway, we will discuss over here the two methods as has been told here. The first method, what is this one? This particular method, here say what is has done, that he applied dimensional analysis to an infinitely long bearing. And this particular analysis, as it is given over here, incorporates a side flow correction, because you understand may be long, but due to the pressure the oil might be leaking out from the sides, and that is what is called the side flow correction factor obtained from the experiment of Mackey and Mackey. This is what we are mentioning earlier as Mackey brothers. So, S. A. Mackey and T. R. Mackey, they are responsible for all those experiments of friction what we have just seen. Now, here a coefficient of friction F is defined in terms of this parameters. This we have seen the bearing characteristics number, then D by C is the diameter of the journal, and K is the, and this is the difference bush and journal difference. I think it is difference in something like that, as difference in bush and journal diameter, and K is some factor. So, what you understand that pressure on the bearing, projected area P by L D, that I have already explained, length of the bearing, diameter of journal, speed of the journal, absolute velocity. So, all these terms are known to you. Only this K is a side flow factor, what is 0.002 for L by D, ratios ranging from 0.75 to 2.8. Now, here this particular expression of friction can be used for determining the coefficient of friction, as I just told you, and this is called as the Mackey equation for full bearing. So, you know the full bearing means not that entire 360, this entire sorry. So, entire 360 zone has been taken into account. Okay. So, if it is half bearing, something like that, somewhere the entire bearing may not be onto the bush system, it can be somewhere like this also. Okay. So, this is other things what is called an half bearing, etc. Now, you can see a factor 473 divided by 10 to the power 10 is being present over here, and that is basically a constant, but this this constant actually is dependent on what? This constant is dependent on the units. So, this constant here mentioned in FPS units. So, if you use the other units like SI units, this requires a change. So, that is the reason be careful that this is given in a shaded zone. Okay. That means, this constant has to be verified depending upon the units of you are choosing. So, now what happens that the steps for the first method, known design parameters are bearing load, journal diameter, journal speed. Okay, this is you have to provide from your from your operating conditions. Then how you design the bearing? So, you have to know the L by D ratio, bearing pressure C by D, also that bearing load has to be calculated, and corresponding bearing pressure also is required to carry this load, and the dimensions also C by D ratio, proper lubricant and an operating temperature. Now, in this case I just have mentioned one important thing, that all these L by D ratio, bearing pressure, C by D ratio, proper lubricant, operating temperature. These are all available in standard design handbooks, where various ratios of L by D and corresponding pressure, what should be the clearance ratio C by D, the lubricant properties, its temperature of evaporation, etc., the best operating temperatures, all these things are nicely tabulated. Now, in this particular one, as I am giving an overview of the bearings, there is no scope as a matter of fact to include all these charts. So, the idea is that you refer to a design handbook and selected design parameters means these are the design parameters combinations for which you will find basically what you will be finding out that mu n by p that I am just describing in the next slide. Now, the value of mu n p should be within the design zone, no explanation required, it is already we have seen. Mackey equation is used to compute the value of friction coefficient of friction f. So, once you know the f, the this particular handbook or the handbook will show you the expressions required to find out heat generation and also heat dissipation, okay, depending on the bearing dimensions, lubricants, etc. So, this is required for thermal equilibrium, means whatever the heat generated should be properly dissipated, otherwise the continuous heat generation will take place. Iteration is required if thermal equilibrium is not established, that is very important, the thermal equilibrium has to be established. Next, the provision for external cooling is required if it is difficult to achieve thermal equilibrium. In certain cases, no matter whatever iterations you perform, it will be very difficult to obtain the thermal equilibrium. So, in those cases an external cooling devices are always recommended. So, this is the brief idea of the bearing design by the first method. Now, if we look for the second method, this method is again based on hydrodynamic theory of lubrication, and this method gives one idea is that the Sommerfeld in 1904 gave a solution of Reynolds equation assuming no side flow. So, that particular solution if we look to, then we find out something like this, that this is the total expression of the solution, where if this particular one a functional relationship what Sommerfeld has obtained for different bearing different types of bearings. Now, here you can see this particular equation or the solution is a very potential one, because you can see it includes bearing dimensions, it includes the friction, it includes the viscosity, it includes that speed of rotation, pressure, but only thing it do not contain is the bearing arc. That means, what is happening this particular how much is the bearing arc. So, that is not taken into account. So, that is the reason this functional relationship can be obtained for different assuming different type of bearings, means 360-degree bearing, 60-degree bearing, that means full bearing, half bearing, 1/4 bearing, like that. Okay. So, this idea is utilized by the Raymond and Boyd in their some solutions. So, what is that? So, this one again, this bracketed term is called the Sommerfeld number S, which is a dimensional number. Here you can see this is the bearing characteristics number what we have already discussed earlier. This is inbuilt in the Sommerfeld number. Now, if we come down, the basic idea of the Raymond-Boyd explanations, the methodology for this bearing design, that what is that one? Raymond and Boyd in 1958 just given methodology, which is basically a computer aided solution of Reynolds number some iterative techniques has been used, and of course, this particular solution is dependent on types of bearing, means for different kinds of journal bearings the solution is solution exists. What are those things? You can see for L by D ratios of 1, the L by D ratios of this thing 1, 1.2, 1.4, and for bearing angles 360 to 60 degree. Okay. So, that is the full bearing coming down to the 60 degree bearing. Okay. So, for all these data, all these sorry not data parameters, one L by D ratio and bearing angles, means beta angles, what is normally being called, extensive design data are available. Okay. These design parameters in dimensional form are defined with respect to Sommerfeld number in the charts. Means we will be finding out various charts he has prepared. This Raymond and Boyd have prepared different charts depending upon various design parameters, and once you consult the chart, then we get the idea of the design. Now, here all these charts are for 360 to 60 degree bearings, because as I told you, the bearing arc was one which did not which was not considered in the Sommerfeld solution. So, for different bearings arc lengths, it has been solution has been obtained. You can have this reference for this particular work, a solution for the finite journal bearing and its application to analysis and design, part 1, 2 and 3. And this was in turn transactions of ASLE and so on and so forth. So, what are these particular design parameters, what we are interested for? So, these design parameters are as shown here. So, these are the design parameters as per Raymond and Boyd. H 0 by C is the minimum film thickness, R by C by F, that is called the coefficient of friction. All you can see are all non-dimensional. Q by R C N L, this is a flow parameter, means we need to know what is the amount of lubricant flow that has to be that should pass through the bearing passage. Q by S by Q is flow ratio, P by P max, maximum film pressure ratio, theta P 0 in degrees, terminating position of film, theta H 0 in degree, minimum film thickness position. As a matter of fact, all these design parameters are based on to this particular figure. You can see this is a journal bearing, this is the eccentricity, and you now by now you understand that when a journal bearing is operating, it cannot operate in a concentric manner, it has to be an eccentric, otherwise no wedge will be formed, thereby no load bearing capacity will be developed. Okay. So, this is the minimum film thickness H 0, its location, this is the P max you measure from the theta. By the way, just have a note that this particular pressure is only for the positive part of the bearing, all right, where you are having this converging zone. The negative part has not been shown in the picture, because that is not of our use. So, this is the theta H 0, the position of minimum film thickness is degrees, theta P 0 is the terminating this particular position of the pressure, terminating pressure, and this theta P maximum is the maximum position where the maximum pressure is generated. So, you can see there is an 1-to-1 corresponding between this particular one and this is this theta P 0, I told terminating position of film. Okay, that is the terminating position of the film, theta P 0. So, that you can see there is an 1-to-1 correspondence between this particular figure and the parameters. So, utilizing those parameters, one can have all those design ideas, all right. So, this gives you the some ideas of the burning design of the journal bearing. Next, let us concentrate our idea onto the rolling contact bearing, and this are of the two kinds. One is called the ball bearing, another is called the roller bearing. So, out of these two kinds of bearings, both are in use, and it has and where it will be used are being very well defined in the design handbooks, and we will have a brief review of this particular types of bearings that are normally being used. So, let us see a typical figure of a bearing. This is called single row deep groove ball bearing. So, we can see this is the bearing. This is called, although everything has not been specified over here, this outer ring, and this is the outside diameter as has been shown over here, outside diameter, extreme ends. This is the inside diameter, and these are the balls. We can see the steel balls are there, and this is called a retainer which keeps the steel balls in position. This is called retainer, and this are the this groove type of situations are the inner ring of the ball race. Similarly, you will be having an outer race of the ball race, this ball race. So, normally what happens in the bearing, the design is being made that outer ring, this outer ring having an outside diameter, this is actually placed inside a bearing, what you call the bearing holder or the bearing block, and this is the inner diameter onto which the rotating shaft is assembled. Okay. So, that means for this one you require to make some sort of seat on the shaft. So, these are the seat. Okay. So, this is here the bearing will come and fit over here. So, that when the shaft rotates, the inner race rotates and outer race is always within the bearing housing. So, this is in the bearing housing, and this is having the rotation. Now, this one is just an figure which shows that how we represent a bearing in the drawing. So, this is the representation of the bearing in the drawing. This is the ball, this is the outer diameter, this is the inner diameter, this is the width of the bearing, and that is this is the width of the bearing where it has in this particular actual figure. And this name again I am just telling it, single row deep groove ball bearing. These are the deep groove ball bearing. This is mostly meant for radial loads, but it can take up considerable amount of axial load too. So, we go down to other bearing. This is called the single row angular contact ball bearing. These are mostly used for radial load and for also for heavy axial loads, because you can see that is here in this case this particular configuration allows you for an axial load transmission. Next, we go for double row angular contact ball bearing. The same kind of thing, having two rows of balls, where you can see these retainers are very nicely placed, and the one thing is that axial displacement of the shaft can be kept very small even for axial loads of varying magnitude. Means if there is an reciprocating load in the shafts, as we have seen in the design, still the displacement of the bearing housing and the shaft can be kept small utilizing this double row angular contact ball bearings. The next one, we can have a single thrust bearing. this is purely for unidirection axial load. So, when there is a pure axial load, you can utilize this sort of thrust bearing. You can see that if goes to the bearing axis, then these are the balls. Suppose this is in the this is suppose this is actually what is happening, that this particular one, if is in the housing and the load is falling onto it. So, these are the tip positions over which this particular bearing can rotate. So, these are used for single thrust ball bearing for unidirection axial load only. Now, you come down to this is the taper roller bearing. This is also another kind of bearing. This is roller bearing having a taper type. You can see this configuration of this one as shown over here and shown over here. So, these are the things what is being represented over here. And this is also as usual the drawing representation of this particular bearing. And you know this typical feature of the taper roller bearing is that for simultaneous heavy radial load and heavy axial load. So, these are one kind of bearing which are used for the purpose just mentioned. Anyway, I think at the very beginning we started with the ball bearings, and this is a kind of the idea which are having the roller bearing. So, that is the roller, this is a length in this way, but anyway in this particular case it is in the tapered manner. Then we are having the spherical roller bearing, and this particular bearing has got a self aligning property. This is for the heavy radial load as is being mentioned. Considerable axial load in either direction can be also applied onto these bearings. The next one is a cylindrical roller bearing. So, either earlier we have seen the rollers were tapered in nature, and these rollers are basically cylindrical in nature. So, these are used for heavy radial load, for high speed use, and within certain limit relative axial displacement of shaft and bearing house is also permitted in this particular type of roller bearings. So, you can see the roller bearings are normally used for heavier load, because ball bearing has a point contact, and in the roller bearings we are having a line contact. So, thereby the contact area means contact location is increased, and thereby it has a capacity of more load. Now, some of the important definitions of rolling contact bearing selection. Okay. So, these are certain important definitions what we understand. However, the word rolling contact bearing selection, also rolling, and this particular idea of the rating life and other things also comes into picture. Well, before starting of this one, so now what I just would like to say that just now we have seen the types of bearings. What are those? The ball bearings and roller bearings, and these roller bearings are having higher load capacity compared to what we are having in the ball bearing, and various kinds of bearings have already been showed to you. Now, one of the very important part of the bearing is coming out to be an rating life. What is rating life? The definition says like this: this is the life of a group of apparently identical ball or roller bearings in number of revolutions or hours rotating at a given speed that 90% of the bearings will complete or exceed before any indication of failure. Now, let us look into the idea. What is that? Suppose we consider 100 bearings, okay, all 100 bearings are put onto a shaft and it is rotating at a given speed, all right, and it is acted upon by some load also. Now, when you see that when these bearings are rotating, then all the bearings will be performing its operation. Now, after some time we see 100 bearings were altogether there. After some time we see one bearing failed, okay. Then we see the second bearing failed, then we see third bearing failed, and so on and so forth. Then what will happen? When the 10th bearing fails, we stop the experiment. We see what is the number of revolutions. That means, that is the number of revolutions the bearing life will be something like that, what we call as an L10 life. That could be in number of hours or in number of revolutions. So, once again to read it, this is the life of a group of apparently identical ball or roller bearings in number of revolutions or hours rotating at a given speed that 90% of the bearings will complete or exit before any indication of failure. So, here 90% bearings were perfectly all right after going for the this thing one. So, that is what we call as L10 life. Okay. So, this is your L10 life. So, obviously, this will be very small. So, if we see 50% of the bearing, then this is median life, it will be much more larger. So, normally people can go for L10 life in general, or other medium life etcetera are also quite common in selection of the bearings. Then we go for another definition, what is called bearing load. Now, it has been seen that if two groups of identical bearings are tested under loads P 1 and P 2 for respective lives of L 1 and L 2, then a relationship stands like inverse relationship stands like that with an power to the power a, L 1 by L 2 equals to P 2 by P 1 to the power a, where L is the life of the bearing in millions of revolution or in hours, either of these two, and a is a constant which is 3 for ball bearing and 10 by 3 for the roller bearing. So, we consider one interesting situation, that this is a basic load rating. Now, this basic load rating is that load which a group of apparently identical bearings can withstand a rating life of 1,000,000 revolutions. So, we can see that if we consider in our earlier expression that either L 1 or L 2 becomes what you called 1,000,000, then what happens? We consider the corresponding load as C, and this is called the basic or dynamic load, and corresponding P is this one and corresponding life is this one. Now, what physically it interprets? Means what you are telling, that bearing will have a life of only 1,000,000 revolutions. So, if it is only 1,000,000 revolutions, for which what is the basic load rating? Okay. So, thereby what happens, the dynamic load rating, if the load at which the bearing fails only in one revolution should be very high. So, normally in practice, if you are having a load P, then we will find that load P for whatever the life of the bearing you choose, this value of C will be very, very high. So, this particular factor or the basic load rating really do not fall onto a bearing. This is a conservative side, that means we are designing a bearing. So, basic idea of the designing of the bearing you will see just right now, that for a given load and given life, what you have prescribed for your application should yield some value of this C, and this value of C should be lower than what has been given by the manufacturers in their catalog. And normally, as I once again to repeat, that this basic load rating or the dynamic load onto the bearing as being prescribed by the manufacturer is sufficiently high compared to the normal load. So, the chances of failure will be relatively less. Now, if we consider the other ideas, that is the equivalent radial load. Now, here is a formula which gives an equivalent radial load. What it means? A bearing can be simultaneously under operation of radial load as well as an axial load. So, what should be the equivalent load is the thing of which is being mainly described through this particular equation. Now, what is this equation suggests? This equation suggests that PE, this is a P equivalent load, will be nothing but V peer or PE equal to x into V peer, this is a radial load, and PA is the axial load. Now, V is the rotation factor. Normally, the bearing rotates in which way? The inner race or the inner ring rotates and outer ring is stationary in the housing. In that case, V has got a factor of unity. If it is other way round, then V has a factor of 1.2. Now, again you can see x a radial factor as mentioned over here, x is a radial factor and y and axial factor. So, in these two cases what is happening, that you have to find out the values of this x and y, and these are normally found from a chart. Here I am not again giving you the values, just I am showing you a typical format of the chart. Okay. Now, this is typical format of the chart to find radial load factors. You will find this type of chart is there and values are listed over here. First of all, you can see that you require a PA axial load, that is known to you, no problem. C0 is what? Actually, what happens, a C0 is a factor which one has to find out from the bearing catalog. How? Once you find out the basic load rating, corresponding to the basic load rating, you will find another factor called C0 is being prescribed over there. Now, looking at that particular factor, what you can consider the value of C0. So, this will give you a PA by P0, corresponding to that you will be getting an value of E, some arbitrary constant E. If this E is greater than this particular factor of axial load by radial load, you choose the x and y value from these two columns. Otherwise, you choose the value of x and y if this E is less than this value of PA by R. So, this type of charts are available in the design book or the manufacturer's catalog, from where one can find out the radial and axial load factors. So, what is this idea? Then let us come down to the selection procedure. Now, what is this one? Depending upon the shaft diameter and magnitude of radial and axial load, a suitable bearing is to be chosen from manufacturer's catalog. I think you this way you do not have any problem of this statement. First of all, of course, you have to find out the shaft diameter. How the shaft diameter is found out? Depending upon your machine element design, what we have discussed so far. So, shaft diameter cannot be altered, that has to be there for carrying a certain amount of load. Now, you know what is the amount of radial load and axial load that is acting onto the bearing. So, from that, knowing the shaft diameter, you can find out from the manufacturer's catalog that what should be the diameter of the bearing. Now, you know, in this case I would like to suggest you one thing, that you know the radial component and the axial component. So, automatically you can find out that what type of bearings you are going to use. Either it will be ball bearing or a roller bearing or something like that. But here one thing is to be mentioned, that the expression for equivalent load what has been described here is for normally for the bearings having more of the radial loads. little changes comes in equivalent load calculations for the taper bearing, but the ideas are more or less the same. So, what is happening that you choose a typical bearing, say single group ball bearing, single row deep groove ball bearing you have chosen, and then that in that particular catalog you find out that what should be the bore size of the bearing, so that it fits onto the shaft diameter. Well, then you have selected that bearing, then for that particular bore diameter you will be getting all the dimensions of the bearing and also two factors. One is the C0 factor, that is, and another one is the C factor. Now, once you get the C0 factor, then immediately you go back to that expression from the chart to find out x y, and then in the subsequently you can compute that load P e. So, once you find out this equivalent load, then you can compute the value of dynamic load rating for the given bearing life, because you know C equals to P into L to the power 1 by A. So, from this expression you can find out what is the value of C. Check the value of C with the manufacturer's catalog. Selection is accepted if C is within the prescribed catalog value, else iteration is required. So, in this one I think now you have understood that how you can have the simple way of design procedure. I think it is not the correct word, I have written here selection procedure, because normally we are not going to design a ball or roller bearing, we are going to select it from the catalog. So, what in nutshell it appears for the rolling contact bearing? There are various types of bearings depending upon the radial load and axial load, or its combination, light, heavy, whatever may be. You can choose either a roller contact bearing, roller bearing, or you can choose a ball bearing. Now, once from these definitions we find out that basic load rating is something defined by P into L to the power 1 by A, that expression, where P is actually to be determined as an equivalent radial load, for which we require two factors x and y. Where from you get the x and y? So, stop at this moment. You find out the type of bearing depending upon your load conditions, and then you find out that manufacturer's catalog, the type of bearing you have selected, then the size of the bearing you select. Once you have chosen the size of the bearing from the manufacturer's catalog, you will be finding out the value of C0 and C. C0 will be utilized to find out the equivalent load. Use that equivalent load means equivalent radial load, and the life of bearing, it is your choice, your design, I mean your idea. So, that life of the bearing in revolutions, number of millions of revolutions, you put it in the expression, find out the dynamic load capacity, check with the manufacturer's catalog, it should be satisfying. If not, then go for a higher size, and why not lower size? Of course, you can go for a lower size. The basic idea is that you go for a lower size, in that way you require to change on shaft diameter. If you go for a higher size, you require to go for a shaft change in the shaft diameter. Well, those are certain things you have to take care in the design of the shaft and manufacture of the shaft. So, this is the idea. So, all these combinations will lead to the final design of the shaft. Okay. So, not only strength criteria, not only stiffness criteria, selection of the bearing, material, all those things are to be chalked out before it is put to the final manufacturing form or in the assembled form. So, this ends our lecture on design of shafts. Thank you.
Dear student, let us begin the lectures on machine design part 1. This is lecture number 36, and the topic is design of cylinders and pressure vessels. Now, this is the first part of the lectures on the same topic. Now, cylinders and pressure vessels, they are one of the very important components of modern day machines. There are number of equipments used in machines which are made in the shape of cylinders, and they contain liquid or gas with high pressure. So, it is very important to design them properly, because as I said, they contain pressurized liquid. Sometimes they may be chemicals which are toxic in nature. So, a failure of such component leads to disaster, that may be the loss of life, property, and many other things. So, the design of cylinders and pressure vessels is very important. Now, we are going to begin the discussion. Now, first the classification of cylinders. Now, cylinders cylinders, they are very well known, that is, this is the cross section of a cylinder. If you look at here, so this is the internal diameter di, and this is the external do, and this distance is the thickness T. Definitely T will be equal to do minus di divided by 2. Now, cylinders are classified according to various criteria. One is according to the thickness. Now, if this T, that is the thickness of the cylinder, is much small compared to that of di, that is T is very much small compared to di, then we call this to be thin cylinders. Now, how much small? Then the practice is T by di must be less than 0.1. So, the thickness of the cylinder, if it is lesser than 10% of the internal diameter, then we call this to be thin cylinder. Then if this is not satisfied, that is T is sufficiently thick, then we call it a thick cylinders. Now, in this class we are going to discuss the thin cylinders. Remember, in the thin cylinders the thickness is very small. So, according to end constructions, now there is another way of classifying the same cylinder. One is the closed ended. Sometimes we have the cylinders which are closed ended. So,